Hi, everybody. Welcome to week 2 of our online distance learning. We're going to continue with our work in Unit 9, which is going to discuss how to find the least common multiple and greatest common factor of different terms. You're going to see that these two concepts are pretty similar to each other. We're going to start off with talking about how to find the least common multiple, aka the LCM, and then we'll take a look at how to find the greatest common factor, aka the GCF. So least common multiple, it's a very similar concept to greatest common factor, but it's one we're going to use pretty minimally here in this chapter. It's something you'll use a lot more next year in Algebra 2. Reason being is least common multiple is typically used while finding common denominators of fractions. We're going to see a little bit of that as we get towards the end of the year in Algebra 1, but Algebra 2, you're going to do a lot more with this as you work with fractions that have denominators that have expressions like x squared plus 8, x minus 2. You'll do a lot of stuff with LCMs in them. So I'm going to show you a quick review of how to find the LCM. So in order to find an LCM, again, we are looking for the least common multiple. So we're trying to find the first thing that both values or any amount of terms can multiply to. So honestly, the easiest way to do it, and it's probably a very elementary method, is to use skip counting. So if we take a look at the first example here, we have the numbers 16 and 48. Here's the way I like to organize this. Now, when it comes to finding LCMs, some of you could probably do this in your head without really having to show much work. If you're not great at your quick mental math multiplication, it might be helpful to write these lists out. Again, it's just up to you as to how you want to do that. But if I want to find the least common multiple of 16 and 48, what I'm going to do is I'm going to start with the number 16. And in my head or on the calculator, I'm going to make a list of the first handful of multiples. So that means I'm going to do 16 times 1, which is just 16. So I'm just going to start with that. 16 times 2, 32. 16 times 3, 48. Now, what you'll notice is if I count by 16s, I run into the next number, 48. What that means, I already have a number in common with both of my values. The 48, I could just do 48 times 1, which is 48, and I can stop both my lists. What that means is once I find the first number in common by skip counting or doing that basic multiplication, I found my LCM. So the LCM of these two values would be 48. Now sometimes you'll get really easy values where you can count up a few times with one number and it'll match the other one pretty quick. Sometimes that's not the case where you're going to have to skip count for both numbers or all the values that you're given in order to figure out what is the first common multiple. You'll see that here in the second example. So we have 5, 7, and 14. So in these cases here, so I'm going to start with 5. 5 times 1 is 5. 5 times 2, 10. 5 times 3, 15. 5 times 4, 20. 5 times 5, 25. I recommend doing about 5 at a time, especially if you're going to do this skip counting method, because that way you don't have to make lengthy lists for no reason. A lot of times you can find it within 5 or so numbers. If not, you could obviously keep going. So I'm going to count by sevens. So 7 times 2 is 14. 7 times 3, 21. Times 4, 28. Times 5, 35. So far I have nothing in common. Now we're going to go ahead and count by 14s. So times 2 is 28. Times 3 is 42. Times 4 is 56. And times 5 is 70. Now, if I look at all three lists, in order for an LCM to exist, it doesn't matter if I give you 2 numbers, 3 numbers, 100 numbers. You have to have the same multiple in all of your number sets. So I currently don't see any numbers in common with all 3 sets, so I'm going to keep going. So I'm going to count by 5 some more. Times 6 is 30. 5 times 7, 35. Times 8, 40. Times 9, 45. Times 10, 50. Do the same thing with the 7s. 7 times 6 is 42. Times 7, 49. Times 8, 56. Times 9, 63. And times 10, 70. Now, the 14s I could theoretically keep going with here. But if I look so far, I still don't see a number in common with all 3 of these. Do you know what? For the sake of just being consistent, if I keep going by 14s, I'd get 84, 98, 112, 126, 140. I have nothing in common with all three sets still. So this one takes a little bit longer, and especially when you try to find three numbers or more, it's going to take a little bit more work sometimes. So if I keep counting by fives though, you'll notice eventually I finally get a common number with all three sets. 70. Takes a little longer, but we get there. So if I skip count, 5, 7, and 14, the first number I run into is 70. That means my LCM is indeed 70. That's the least common multiple for all three of these values. Now typically ones that you'll be given, you won't have to count necessarily that far, and most of the time you go two at a time. But ultimately you can do this with more than two sets of terms. So now, let's use this here to talk about terms with variables. So here in number 3, I have 12x squared y, 18x cubed, y squared z. First thing I'm going to do is I'm going to rip off the coefficients. So I'm going to worry about 12 and 18. So I'm going to count by 12s. So you can see this list here, 12, 24, 36, 48, 60. If I count by 18s, 18, 36. Hey, look at that. I've got my LCM of the numbers, so I'm going to start off with that. Okay, so start off with the common multiple of the coefficients. Now we're going to take a look at the variables. So if you look up at the top, pretty blanket statement if you look at the top of the screen. Multiples are larger, so the LCM includes the highest power of each variable. So think of it this way, you're counting up to get your common multiple. So when you look at your variables, you want to go up to the highest variable in terms of the highest power so that you can include everything. So I'm going to compare between each term. I have an x squared and an x cubed, so I'm going to look at each common letter. So I want the higher of the two for the common multiple. Higher of x squared and x cubed would be x cubed. Then I'm going to compare the y and the y squared. Well, the higher would be the y squared. Now, we still have a z that hasn't been used. So the first term had nothing. There were no z's. The second term had a z. Well, z is higher than nothing, so we're going to include that. Here's my LCM, 36, x cubed, y squared, z. So we're going to count up with our numbers, and we're also going to take the highest of each variable that exists. Here would be a great point if you want to try numbers 4 and 5 on your own. Hit the pause button and then fast forward. See where you're at, see if your answers make sense to mine. If you want to watch another example here, I'm going to explain the other two at any rate. So let's take a look here at number 4. We got 18 ab to the 4th c squared and 27 ab cubed c. Let's start with our numbers. So I'm going to count by 18s. I'm going to count by 27s, and right off the bat, I run into 54. So the LCM of the two numbers is 54. Now I need the highest of each variable. So we'll compare the a's. I have an a and an a. Well, they're both the same, so a is the higher of the two, since they're tied in value, if you will. I have b to the 4th and b cubed. B to the 4th is higher. C squared and c squared is higher. So my LCM would be 54, a b to the 4th, c squared. Now, last but not least, same type of question here, number 5, just as a multiple choice. So let's start off by finding the LCM of 32 and 20. So I'm going to count by 32s. Now I'll count by 20s. So if I do 5 at a time, I don't get anything in common right off the bat. But if we use some logic here, if I look at the number 20, 20, 40, 60, 80, 100, if I just keep counting by 20s, I'm going to run into 160. Okay, so my LCM is going to be the 160. So from a multiple choice perspective, A and B are bad answers. And we'll talk about how you would get that too in just a minute. So now my choices are between C and D. Again, for my LCM, I need the higher of my powers. So the higher between n to the 4th and n cubed is n to the 4th. The higher between n squared and n squared remains n squared. C would be my LCM. So again, the long and short of it, to find the LCM, we're counting upward, we're counting by multiples, and to find the first number in common, to find it with variables, you're again counting upward. You need the highest of each variable, no matter how many terms you are combining. So that's how you find LCM of different values. Now we're going to take a look at something that we're going to work with a lot more in this class and in this unit specifically as we move forward, greatest common factor. So LCM, we count upward and multiply. Greatest common factor, we're going to try to divide and find what divides into a set of terms. So there's a couple of different ways that we can do this. I'll show you the long way, and then ultimately, for my hope for most of you, is that we use some mental math to find quicker ways to divide in, since division can sometimes be a little bit easier than multiplication in terms of breaking the numbers down. So if I want to find the greatest common factor, you might remember this from earlier in the school year. We kind of did the same strategy when we broke down radicals and square roots. If I want to figure out a greatest common factor, what we're going to do is figure out what's the biggest thing that divides into each of these numbers. So you can either try to do that mentally for right now, or you can make factor trees. So I'm going to take 39 and break it apart. I'm going to take 6 and break it apart. So if I break 39 apart, it's 3 and 13. If I take 6 and break it apart, it's 2 and 3. You're going to do prime factorization trees for each of your terms, if this is the strategy you want to use. We are looking for what's in common from each tree. So I see a 3 in common with each tree. That's the biggest number that'll divide into both 39 and 6. So my GCF is 3. Now, you can use that strategy ultimately as we go throughout. You'll notice we'll use GCF a lot more in the upcoming sections, where I won't be drawing factor trees all over the place, but if you struggle with, again, breaking down some of these numbers and doing some of that division in your head, this is ultimately a way that you can do that. That's the way I'll probably go through most of these here, so you can see how some of these common numbers break down. Now, when I throw variables into the mix, so least common multiple, we went and found the highest of the exponents because we're counting up. Since we're dividing down in GCF, we're going to take the smallest power of each variable. So I'm going to do the same thing like I did with the LCM. I'm going to worry about breaking down the numbers first. So we're going to break down 20 and 29. 20 breaks down into 4 and 5. 4 breaks down into 2 and 2. 29 is prime. So the only way that's going to break down is 1 and 29, over and over and over again for infinity. Since dividing by 1 kind of useless, we're not going to worry about breaking it down. So if I look at these, I don't see any prime factors in common. That does not mean it doesn't have a GCF. It just means the GCF numerically between these two numbers is 1. So I can always divide a 1 out of each of these terms, no matter what. Most of the time you'll find something that's bigger than 1, but if ultimately there's nothing in common to divide out, that means you divide out a 1. Now we're going to take a look at the variables. So we have x cubed and x squared. Again, the short version of this is I'm going to take the smallest of each variable. So that means I want the lower exponent of those two variable terms. So x cubed and x squared, what is the lowest? It's x squared. So I can write my GCF for this as 1x squared. Technically, if I have a 1 taken out, I don't need to show that. So I could also just write this as x squared. And that is my GCF. So again, this is a good point here. If you want to pause, try the next couple, see what answers you get using this as a model. Feel free to fast forward to see the answers. If you want some more explanations, again, continue to watch here, and I'll work through the rest of these. So here we have a number 8. We're going to break down the 45 and the 60. Now remember, when we do these prime factor trees, there are sometimes multiple ways that they can be broken down to start, but ultimately you end up with the same prime factors at the end. So 45 breaks apart into 5 and 9. 9 breaks apart to 3 and 3. 60, that can break apart into, let's go with 10 and 6. 10 will get you 2 and 5. 6 will get you 2 and 3. So I see a 5 in common, and I see a 3 in common. If you're going to use this method, if you have multiple factors in common, you'll multiply them together. So the 5 and the 3 will get multiplied to get you a GCF of 15. And again, think logically. 15 is divisible out of 45 and 60, so that works. Now, in terms of the variables, we're going to go ahead and pull the lowest of each. So comparing a squared and a, the lowest is a. B cubed and b squared, the lowest is b squared. Now we have an instance again where there's a c in one of the terms, but there's no other c in the other term. Again, we want the lowest of each. So if I have a choice between nothing and c, and I need the lowest, I'm going to choose nothing. So my GCF of these two terms would be 15ab squared. And last but not least, let's break apart the 120 and the 80 in number 9. So 120 will break apart to 10 and 12. We can see how 10 breaks down. 12 will break down into 2 and 6. We know how 6 breaks down. So 80, that can break apart into 10 and 8. We know how 10 breaks down again. 8 is 2 and 4, which gets me 2 and 2 when I break down to 4. So the GCF, let's look at what's in common. So I see a 2, another 2, another 2, and a 5. So I'm going to take 2 times 2 times 2 times 5. My GCF of these two numbers is 40. And again, if you want to check your work, make sure, go with your calculator, divide 40 into both those numbers. If it comes out evenly, you're in good shape. Now let's take the lowest of each variable. So x squared and x to the 4th. I'm going to take x squared. Y and y to the 7th. Y is the lowest. Z to the 5th and z squared. I'm going to take z squared. So the GCF of these terms would be 40 x squared y z squared. Last but not least, so same idea here, number 10, you've got a multiple choice version of this. So we're going to break down 12 and 18. So another way we can break down 12 is we could do 3 and 4. And then get 2 and 2 off of the 4. 18 breaks down into 3 and 6. And we know how 6 breaks down. So we got a set of 3s and a set of 2s. We multiply that together. The GCF of those two numbers would be 6. So that eliminates A and B. Now it's just a matter of pulling the right variables. So again, I need the lowest of each. The lowest of the x's, I have x cubed and x. Pull the x. The lowest of the y's would be y squared. The lowest of the z's would be z. Once again, my answer is C. That is indeed my GCF. So the big difference again between the two. If I'm finding an LCM, I'm counting upward. I'm finding the highest of each variable term. If I want to find the GCF, I'm dividing down. I want the lowest of each variable term. LCM, again, is something we'll use a little bit as we go through the rest of the year. Primarily, though, we're going to use a lot more of GCF over these next few weeks. So, if, again, you have any questions, feel free to shoot me a message, get a hold of me. I'll be more than happy to explain anything in greater detail. Make sure that you can practice these here and that you understand what you're doing before you attempt the Schoology assignment that goes with this. Please make sure, again, you complete and submit that by the deadline that I've set. Thanks for watching. We'll see you next time.